Okay, why don't we get started again? I need to finish by 12:15 so you can all take the walk to basically the club where lunch is, the Tiger Club, where you're going to have lunch. As I said, the third part I want to talk about has to do more with measurements. And I want to particularly show you the complexity of the environments that typically measurements are made. You know, one of the nice things where we need additional work is diagnostics. But as I mentioned, diagnostics are going to be very complicated because, just as I said, if I'm looking at an AP composite propellant and I want to know something near the surface is going to be three-dimensional on the length scale of the flame, and it's also going to be transient. Because as the flame goes down, it's going to all of a sudden see a big AP particle. That AP particle is going to disappear. So I've got this very complicated three-dimensional transient problem where I want to try to get diagnostics so that I can build kinetic models so that I can start doing predictions. I mean, there are kinetic models that people have developed, and I'll talk more about those tomorrow. Okay, so far, as I said, we've looked at different types of components, learned a little bit about composite, heterogeneous propellants, and homogeneous double base type propellants. I've showed you probably one of the important relationships that go away with is that the burning rate of a propellant goes as the pressure to some nth power, and that nth power becomes very important. I did put an appendix. And as I said, and I'll show later on, in that appendix, it shows why N is very important. If N is larger or near 1, and I have a pressure fluctuation in my motor, then the pressure can exponentially continue to build, and I'll have a catastrophe of the motor. So for, say, most rocket motors, that pressure exponent is 0.6 or less. Okay. If I'm designing an explosive, I obviously want it near 1. Okay, and that's one of the important metrics then is, knowing how, if I develop a new material that I'm going to use as a propellant, I've got to be able to characterize the burning rate as a function of pressure. Okay, and that's one of the things I'll get to. And I'll try to finish all my notes in this session. If not, I'll do it first thing very quickly tomorrow morning. Okay. Burning rate of solid propellants, as I said, we've now seen empirically and also can justify analytically that the burning rate should look like some burning rate coefficient times the pressure to some burning rate exponent. Okay, this equation is valid only when the cross-flow velocity over the propellant surface is low enough so convection effects on the burning rate are neglected. So cross-flow, because I'm going to change the heat transfer back to the surface, it's no longer only going to be conduction, I've now got convection. It's going to change the heat flux into the surface, and as a consequence, I'm going to know the burning rate's going to change. Okay, so what I'm going to be describing right now are linear burning rates that are basically just looking at conduction as the input for the heat release and the heat thermal wave into the depth. So in the case of a high velocity flow of contribution gases over the burning propellant surface, a different equation must be used because now I've got to include basically erosive burning. And I show here basically in the case of two different types of solid propellant motors, not going into any detail. If this is my grain here and this motor on the left, this is the surface I'm going to ignite. This is referred to as an end-burning grain. And here you can see I'm going to have minimal cross-flowing. There could be some, as I note here, this surface initially starts out as flat, but the surface could have some curvature that could lead to a little bit of higher burning rates near the edges because of building a boundary layer. But in a center perforated grain, so if I looked at the grain on length, this surface area is going to look like that the entire length of it. And so if I ignite it at this end, the gas flow is going to come off of this surface and come down this center perforated region out of it. So I will have a cross flow. And the question is, how large is that cross flow? And is it going to change? Is that cross flow going to change with time? Because eventually I'm going to be burning this grain out, and the cross-sectional area is going to get larger and larger. So my overall Reynolds number is going to change inside the motor. Okay, I mentioned burning rate, important metric. A second burning rate for a propellant is what's referred to as the temperature sensitivity of the burning rate. Okay, the burning rate of a solid propellant is dependent on pressure. We know that, P to the N. However, it's also dependent on the initial temperature of the propellant, T sub I, even when the pressure is kept constant. Remember, we just did this analytical analysis, and I showed you A here was not necessarily a constant. It can depend on temperature. In fact, the initial temperature. If I have my propellant sitting out in Arizona, I ignite it, the initial temperature is going to be very hot. If I do this up in northern Canada, it's going to be very cold. I'm going to get different burning rates, and that's important to know because it's going to check it's going to change obviously how the motor burns. It's going to change the burning rate. So as I note here, the parameter A is not a true constant since it can be expressed as a function of the initial temperature T sub I and the temperature sensitivity sigma sub P. So again, this is an empirical fashion I'm showing you here. I'm representing A as some reference value of A times the exponential of this parameter called the temperature sensitivity times the difference between T sub I and a reference temperature for which I have the reference value of A. Okay, and I can then define the temperature sensitivity as 1 over the burning rate times the change of the burning rate with regards to the change in the initial temperature at constant pressure. Okay, and I can bring the burning rate into the differential in the form of the log, so I can have d log R sub B over dt sub I P. Okay, and this is the general definition then of the temperature sensitivity of the burning rate. If I incorporate this now into my VA's law or St. Robert's law for the burning rate, I can write the burning rate then as equal to this reference A value exponential of my temperature sensitivity times the initial temperature minus my reference temperature times P to the N. Okay, and so what is going to become important then is basically determining these values as well as this value to fully characterize a propellant. And what I show here is that the temperature sensitivity of the burning rate also depends on the pressure. So it becomes a very complex set of data, matrix set of data that I've got to collect. And I show a couple examples here. For ammonia dinitramide and ammonia perchlorate, these are just pure components and I'm burning them. And I'm looking at what their value is of the temperature sensitivity as a function of pressure. So I note on the right here, the temperature sensitivity of the propellant burning rate is a function of the propellant chemical composition and usually depends on pressure. As the pressure is increased, generally the temperature sensitivity decreases, as I show here for ADN. This is most apparent in the nitramines, HMX, RDX, and CL20. Ammonia perchlorate has shown an exception to this trend as sigma P first decreases and then increases with pressure. In general, propellant ingredients with low temperature sensitivity are favored because they have more consistent performance under different operating conditions. So I definitely want to have a small value for the temperature sensitivity of my formulation. Okay, burning rate measurement techniques. I mentioned the first one here, which is referred to as probe. It involves inserting wires across a propellant strand and measuring the distance between the wires and as it burns when they break. And it's typically done in what's referred to as a Crawford bomb, which is just a pressure vessel in which I insert this strand. And I'll show you a picture in a second. An improvement or variation on just the probe technique is to use optical measurements, where I also visualize the burning as it propagates down and watch the surface. One of the advantages there is I can actually see, is it burning as a one-dimensional flame, or is the surface, non-linear? Okay, if it looks like it's propagating in cracks like that. So there you need to obviously use a window bomb. This is a direct measurement. Burning rates determined from high-speed cameras taking the data and visually looking at its position from the high-speed data on the film, and simultaneously observing whether or not I have a uniform planar burning, if I have flame spread down the side edges, depending on what the melt, is there residue forming at the surface, is there ejection of particles, and I get a better characterization of what's going on. I can also just monitor the pressure. Suppose I have a pressure vessel that has a certain volume, and I put my propellant inside, I ignite it. Since it's releasing gas, I can basically measure how fast the pressure changes in that vessel. Now, when I do that, it becomes a little bit more complicated because I have to have a little bit of a modeling analysis, and I have to make some assumptions because I have to know what gas is being formed from the burning process. Does those gases go all the way to equilibrium? Or in the vessel, did it not quite go to equilibrium and the number of molecules changes? So I do need to make some assumptions. So here I measure the pressure variation as a function of total burn time based on equilibrium thermochemistry. The burning rate's calculated from correlation that requires knowledge of the specific heat in the heat of combustion, and sometimes it's done in an oil and water bath. I could less crude, but I could also, and this is more maybe for motors or larger systems, I could look at basically the weight lost, or I can measure the thrust. And as I said, it can be applicable to transient burning. I could also use a microforce transducer in measuring this thrust. Microwave reflection interferometry is used. The propellant is bonded in waveguides, and then microwaves are reflected from the surface by ions in the reaction and create a phase shift, which is recorded. Very applicable to transient burn and can be used for aluminized propellants. You can also use an ultrasonic method in which the propellant is attached to a coupling material with a transducer. Mechanical waves then travel from the bottom through the material all the way up to the burning surface, and they're reflected back, and you monitor that as a function of time. And as a consequence of that, it's also applicable to transient burning, most often used in motors. And one can also use X-ray measurements, much like I showed you in monitoring the nozzle earlier. I could have done that in the actual chamber as well. So here's an example of what's referred to as a strand burner. So these are doing just fundamental measurements. If I was making a new material, I would not want to make a large amount of that material first. To characterize its combustion characteristics, I'd want to make as least amount of material I could. And so typically you would do something, as I said, a strand burner, where I put the energetic material in the form of a cylinder. And I'm going to measure the linear propagation rate. So you can see here again, I've got what's referred to as the strand of that energetic material sitting here. It's sitting in a pressure vessel. And in this case here, I have a window, high-speed camera. I ignite the top surface here with, say, some sort of heating device. It could be just a nichrome wire, depending on how much energy is needed. And I might have to put something that burns very fast and ignites easy on the surface so that I know the surface is uniformly ignited very quickly. And I have to worry about, if I ignite the surface, does the flame propagate down the side here? So do I have flame spread? So it not only is burning on the top, but does it burn on the side? And that's one of the values, as I said, of having a window chamber. I can see if that happens. Now, the way I avoid that is what I'll typically do is I'll coat the outside surface here with only a fuel ingredient that has no oxidizer in it. Remember, the propellant has fuel and oxidizer. So in that case, it's going to be very difficult for the flame to propagate down here because I'm going to fill this chamber here with an inert material like argon or nitrogen, so there's no oxygen out there. Okay? And that prevents the flame then from spreading down the side. Okay, so the way I do this, if I wanted to get measurements at a certain pressure, I'd fill this chamber up to, say, if I wanted to know that it's burning rate at 1,000 psi, I'd fill this chamber with 1,000 psi of argon, then I would ignite it. And then I have two options. Is the chamber large enough such that the gas coming from this surface did not change the overall pressure that much? And then I could leave it closed. If it looks like the chamber volume's small, what I would do is, as this is burning, I would control a small amount of inert material coming through it such that I maintain a constant pressure. So I'm getting a burning rate at a constant pressure. So a little bit more detail on the strand itself. So this is a close-up picture of what it might look like. So typically I work with small propellant strands, maybe 50 millimeters long, 6 millimeters in diameter. And as I said, they're designed to burn as an end burning specimen for determining their linear rates under well-controlled pressure and temperature conditions. All lateral surfaces are covered with an inhibitor material, leaving only the top surface to expose. So one of the ones, it's a very common material we use is just nail polish, or you could take just paint and spray it on the outside. The burning rate is deduced by measuring the time needed to burn a fixed length of the propellant, which is the distance between two consecutive brake wires inserted in the strand, or by visual measurements through a windowed strand burner. So if you look here, this is the propellant. On the top of there's a, in this case, this is a gap propellant strand. I don't think it needs another material on the top to get it uniformly ignite because the gap burns very quickly. There's a nichrome wire coming over here as an ignition source. And then you can see at different locations down here, there's a brake wire going through there. You can see right here, there's a brake wire going through. And so I know I measure the distance between that, and I can get then the burning rate from when those wires break. Okay, as I said here, inert gas such as nitrogen is used to pressurize the chamber and is allowed to flow continuously as purge gas during the test. The temperature of the purge gas can be controlled to desirable levels for preconditioning the initial temperature of the strand. So if I wanted to measure the temperature sensitivity to the burning rate, I would basically change that temperature of the gas flowing through there to a higher temperature so that I try to maintain the temperature of the strand at a different value than just ambient. And then a fine wire thermocouple can be inserted in the specimen for determination of the thermal wave profile in the condensed phase. And I don't know, but it would be the fine wire thermocouple would be inserted as I showed you before, and is a complicated measurement. So here's an example of one of the strand burners we have. So you can see it's just a metal chamber. There's windows over here. A camera sits out here to the right. In this case, the camera is actually being reflected from a mirror in case the window broke. But what we would do then is if we took a film of this, we would create an XT diagram from the film. We'd pick a particular location, and from the film we'd know the time, go to another location, see what the time difference was, and we'd make a plot of this XT, and the slope of that obviously is the burning rate. What this tells us right away is if we don't get a linear profile, we know we don't have a steady burning rate, right? And so that data would not be good, and we'd have to understand why it's not burning quasi-steady. I show some examples so you can even see the surface of this burning process can be very complicated, and sometimes the surface is not always uniform. So on the left here is RDX. I showed you an example of that. JA2 here, you can see actually carbonaceous material comes to the surface and it burns like soot particles, but that are attached, carbon particles that are attached. You get this high luminosity from that then. And M43 propellant is basically an RDX-based propellant that has some other material in it. And you can see, again, its characteristics are different than the RDX itself. This is a recent chamber that we built out at Penn State. And the unique thing here is we're interested in going to very high pressures. This chamber goes to 50,000 PSI with an optical window. The optical window is about 4 inches thick. And the reason we were interested in making this device is for two reasons. If I'm looking at building a rocket motor, typically the highest pressures you deal with in standard rocket motors is, and I'll show you why later, is about 2,000 PSI. The standard reference pressure is 1,000 PSI, but you won't find many motors today going over 2,000. Okay? But if I'm looking at a gun propellant, then those pressures go up to about 100,000 PSI. And so this device gives us a measurement getting close to that value, be able to observe how it burns. But our other interest in doing this was we just wanted to look at burning rates of materials at extreme conditions. Because, if you perturb the system and you go to another condition, you might learn something. And you might learn something at that other condition that makes you go back and understand something at conditions you're interested in. So, going outside of the box. And you'll see kind of what I mean by that in a few minutes. But this device, just to show you, this is the strand burner here. The walls are 8 inches thick of steel. The inside diameter is 5 inches and has a length of 3 feet. And so we can put more types of experiments inside it than just strand burners. We can put gas phase systems inside of post burners and a whole bunch of different types of experiments and physically observe what's going on. You can also get a burning rate measurement from what's referred to as a subscale test motor. This is often, the next level of testing of a new propellant beyond the strands. It gets you a little bit closer to what might happen in a real motor. And so small-scale rocket motors are used for propellant screening, development, performance verification, and production control. The nozzle allows assessment of burning rate at a specific operational pressure and over a range of pressures. So if you look at this motor right here, here's the grain. It's in the chamber. And so it's a cylindrical perforated grain. It just has a nice circular hole all the way down the grain. And my nozzle's over here. And so what I'm going to do is on the left-hand side here, I'm going to ignite it. And what I want the flame to spread very quickly down the surface of the grain so that after it's been ignited, it's burning radially outward. Okay. Now the pressure inside here then is basically controlled by the burning rate in the surface area and the nozzle hole diameter. So if I want to do this experiment at a different pressure, I've got to change the nozzle diameter, okay, to change the pressure internal to the system, okay? And that's how I start developing my burning rate as a function of P. And so how do I get a burning rate from this? Typically I'm not looking inside the motor here, so I've got to do this from external measurements. And so the burning rate is often determined by what's referred to as the thickness over time type method. So the web, this distance here is referred to as the web thickness. And initially, since I'm putting the grain in, I know this initial distance, and I'm going to let it burn out all the way to the exit. So I know that distance. And I'm going to eventually measure the time between those two distances. So the web thickness is defined as the minimum thickness of a grain from the initial burning surface to the insulated case wall of the motor or to the intersection of another burning surface. Examples are end burning grain. So in an end burning grain, if you remember, it was just burning linearly down the grain. And a center perforated grain is burning out radially. And so the web thickness has changed there. And the conventional method based on the propellant thickness and the burning time is just to measure the difference between the web thickness burned over the burning time. And if I look at the pressure or the thrust that's developed as a function of time in this motor, what I'll get is something like this. Suppose this is the pressure. So initially, the pressure starts to rise, and that's a consequence of my igniter, right? Because initially, I'm going to put gas in to heat up the surface to ignite it, and that's going to be hot gas, and that's going to start raising the pressure a little bit. So I'm going to start raising the pressure a little bit up here and add pressure to the cylinder inside the chamber. Then all of a sudden, the propellant grain is going to ignite, okay? And then it's going to basically fill the chamber until it becomes choked. And then at that one point, I could potentially, depending on the grain design, I could have, and this is what you'd want in these measurements, is have what's referred to as a neutral burn so that the pressure doesn't change as a function of time until I burn out the web thickness. And so right here at this point, I've reached the casing, there's no more propellant. And the pressure's still high and it slows down because there's still gas pressure inside the chamber, and that's got to be released through the nozzle. And that's what you're seeing here then. And so now how do I define the time of the burning of the grain? And people have used different criteria, but in this particular case, I'm using this definition here being TB when basically the grain has started to burn, and TE here when the grain ends to burn. okay? And so I just basically take the web thickness and divide it by that time. And there's variations on that, how I define that, because, you know, it's a relatively crude measurement. And, you know, how much of this area over here should I include? How much of this area over here should I include from the fact that the grain is burning? Okay, so you can see variations on that. I don't want to spend time on this one, but you can actually, you know, account for those end masses by trying to account for what was burnt early on, what was still left in the chamber. And there's a correction terms by integrating the pressure over time from different times. And you can actually even do knowing mass measurements, just physically doing mass measurements in time itself. Okay, so, you know, if I'm talking about rocket motors, how do I correlate it to full-scale motors? In general, full-scale motors, small-scale motors, and propellant strands do not have the same burning rate at the same pressure, and a correlation or scale factors used to relate them. Various parameters that influence the differences are intrinsic parameters such as the pressure, temperature, mechanical properties, global parameters such as the internal motor flow field, the real grain geometry. As I showed you, it could have slots in it and things like that in which the convective burning could be different at different locations of the surface. Erosive burning, the rheology of the grain manufacture. And then in a motor, there could be other things such as combustion stability, the fact that if it's a center perforated grain, the flow's going down the grain, so maybe the radiative contribution is different than just a strand or in a real motor. Propellant composition at the liner interface, thermoelastic coupling, nozzle design, acceleration, and things like that of a real system versus, you know, a subscale motor. So lab scale strand burner experiments are best for assessing statistically significant effects of formulation changes and validation of modeling and simulation efforts. So it's one step beyond the strand. Some considerations of experimental conditions. As I said, inhibitors used to create 1D burning if you're looking at strand burning. Side burning is prohibited by covering the sides with an inhibitor. Any inhibitor may be used as long as it does not react or dissolve the propellant or interfere with the propellant burning surface. As I said, we've used nail polish as one of the inhibitors. The temperature dependence. Burning rates generally increase with propellant temperature. The sensitivity of the burning rate to propellant temperature must be quantified as well as the effective temperature on pressure sensitivity. Temperature sensitivity appears to be highest at lower pressures, so the pressure effect can be important. You need to do this by measuring the burning rate at a number of pressures, say from 100 to 1500 psi at different initial temperatures, or measure the burning rate at 2 or 3 pressures at a number of different temperatures. So all of a sudden, you know, the idea of measuring a single pressure and burning rate at that pressure becomes a matrix of measurements. So actually quantifying a new formulation takes quite a bit of time in measuring something as simple as a burning rate. Pressure dependence. RCP we know now is dependent on the pressure. You need to have this for a propellant less than 1, somewhere between 0.2 and 0.7. Propellants in solid rocket motors operate at pressures from about 700 to 1500 psi. There's a lot of interest in going to higher pressures as well. There's advantages, obviously, to doing that, but there's also complications, because if I go to higher pressures, I'm going to change my convective heating. So all of a sudden now I've got to worry about heat loss and convection going into that outer surface, okay, and the structural characteristics of the casing and things. So it becomes a coupled system that one has to look at. Experimental measurements at such conditions can be difficult. The premix flame zone is drawn closer to the propellant surface as you increase the pressure, and the final diffusion flame moves further away from the surface. You remember the structure, I said the flame, if I had this, there was this AP pellet here, and this was a little bit of fuel binder, another AP. What happens as I go up in pressure, the AP burns at a faster rate. So it tries to dig down into this propellant. And as it digs down, it basically increases the rate of gas coming off of the surface. And remember, it's the AP that creates the O2 in which the binder out here has to react with. So all of a sudden, this diffusion flame, it gets extended to a higher location at higher pressure, whereas the little particles down here, they can sort of pre-mix with the binder as it decomposes. And this flame right here then becomes like a pre-mixed flame over the binder. And it remains basically the same. So you change the structure of the flame burning process also as a function of pressure. Gas properties not well defined or understood at very high pressures, and optical diagnostics are complicated by sharp density gradients in the flow, spectroscopic line broadening, and the requirements for very thick windows. I told you the windows in that chamber I just built were 4 inches thick, so you've got to worry about those characteristics as well. Erosive burning. It's a modification of the burning rate by flow of product gases across the surface. The cross velocity modifies the energy transport mechanisms to the propellant surface. Obviously, I'm introducing a convection heat transfer process. Erosive burning results in a dramatic increase in the burning rate once a critical Reynolds number is reached. And erosive burning effects do not scale well and are generally less severe with increasing motor size, because if I have a larger motor, typically my burning surface area gets larger, the flow rate, the overall Reynolds numbers can be lower down the center perf. Something that's not considered too much is what's referred to as strain augmented burning. Solid composite propellant strands subject to tensile strain have shown burning rate augmentation once a critical strain values are surpassed, and this is thought to be due to the de-wetting of the particle binder forming voids and the ability for the flame then to propagate into the grain further, and so the surface area is effectively changing. Also, when the propellant undergoes a rapid strain, for example through ignition, or heat is generated in the propellant which modifies the local burning rate, the propellant stress strain response can contribute to variations in the motor burning rate. In quasi-steady versus transient measurements, we've said that the burning rate is a function of pressure and the initial temperature. And if I have variations in the pressure in say my chamber that have some frequency, that's going to basically affect the burning at the surface. And what I'll show you later is it basically depends on the time constant for heat transfer in the condensed phase versus heat transfer in the gas phase, how quick they change with the pressure variation, and also how quick does the burning at the surface change with that pressure. So let me just show you some results here. This is and you can see the effect of changing the initial temperature and burning rate. So I'm making a plot of the log of the burning rate versus the log of the pressure. And you can see for this particular JA2 propellant, which I told you was a double base propellant, I'm changing the initial temperature from 233 Kelvin to 333 Kelvin, so a change of 100 degrees. And you can see overall, the burning rate changes by an order of magnitude over that 100-degree range. Okay. And then as I told you, out of this data, one would try to get a temperature sensitivity parameter. And people have correlated it different ways. So in this particular case, the correlation was set up as shown in this equation here by changing the pressure and trying to back out then what these empirical parameters were to basically condense it down to a simple expression that could be used in the burning rate equation here. Another example for looking at JA2, what happens when I get to higher pressures? Okay, now I'm going to higher pressures than I showed you in the previous at a particular temperature. And notice this is very characteristic of propellants. Notice at low pressures, I have a certain value of N. Then I get to a certain pressure, and this value of N changed. Okay, so down here, these are correlations for the burning rate. At the lower pressure, you can see the burning rate has an exponent of 0.63. And in this region up here, the burning rate has an exponent of 0.97. It's getting close to 1. Okay, so this would be very dangerous for a rocket motor to operate in this range. I'll show you that in the appendix notes maybe tomorrow. So I would have to run, if I was using JA2, all my motors would have to run below this critical pressure here. So knowing if I have a slope break in a propellant burning rate curve becomes essential and where that might occur. We're still trying to understand why those slope breaks occur, okay? And people have given many different reasons, but if you're trying to design a new propellant and you want to operate at higher pressures, you better know its characteristics and whether or not there's slope breaks in that new formulation. Just some more examples of burning rates as a function of pressure. These are pure ingredients, pure oxidizers. So this one here is HMX on the left. I have RDX on the right. Notice at low pressures, again, this correlation is really linear on this log plot, log plot. What's kind of interesting is now I'm getting to about maybe close to 20 megapascals, and I see a slight deviation of the burning rate. And the same thing's true for RDX. I get a little above maybe 15 or so, come up linear, and then I get a little deviation from, but it goes back to a relatively constant value. Why does that happen? Don't really know yet. Models can't predict it. So it's one of the interesting questions that people are still studying. Here's some other burning rates of 6 different monopropellants that are used commonly. And again, this is at pressures under 10 megapascals. So remember when I showed you early on the energy densities of different propellants, I told you that ADN mixed with aluminum was very high. Look at ADN's burning rate. It has a very low pressure exponent and burns very quickly at low pressures. Then HNF is another oxidizer, that hydrazinium nitroformate has a curve here. This is Cl20. RDX and HMX follow each other up to this pressure, and then AP here. Okay, so over this range, some of these look like they have a pretty constant value of N. Look what happens to ADN, pure crystalline ADN, if I go to higher pressures. This is what I showed you on the previous graph. I go to slightly higher pressures. Again, I'm getting close to 20 megapascals, and all of a sudden, it can drop off and eventually come back up to a new slope. Why does that happen? We don't understand it yet. People have given different proposals of what's happening. In fact, this is, if the propellant, this crystalline grain was quenched while it was burning at different conditions, this is what you would see, okay, in these different regions. So in this initial linear region down here, if I quench the surface, and if I quench the surface, that doesn't mean that's what the surface looks like while it's burning either. It could have, changed while it was quenching. But what you see here, in this region, you have a steady planar flame, and the gas seems to be entrapped in a liquid resulting in a froth. I increase the pressure a little bit higher. I still have a steady planar flame, but I start to develop ridges and valleys with activity sites and valleys. So you can see the structure changing. Now when I get into this negative region here, all of a sudden when I quench it, on the surface are needles, okay? And this is where I have an intermittent, non-planar flame that's really unsteady, and I find needles in regions of the maximum regression. And then I go up to this region where I start to get back to this linear rate with a much steeper grade. Again, I have a steady planar flame where the surface now is entirely covered with needles. How does that affect that value of N? Maybe that's a physical process, it sounds like, but is that the only thing that's going on? And what causes that to happen? Here's a very simple example. This is in this case, burning of a liquid propellant. Okay, so when this was done, in the case of a strand, I take basically a quartz tube where I can visually look through it, and I fill the quartz tube with liquid nitromethane. And at the top then I'll put my hot wire, I ignite the surface, and what I do with a camera is the flame now propagates inside the tube, and I watch the liquid surface as it propagates down in the tube, and I can get a burning rate. So again, looked at low pressures, I have a linear burning rate. Again, I get to about 20 megapascals, and all of a sudden I get a slope break, increases, and then it reestablishes value at a higher pressure. Questions as to why this happens. Typically, 10 megapascals in older burners, that was basically the highest pressure people would use with optical chambers. That was one of the reasons I built that new system to go higher pressures, to see what's going on up here, and I'll show you that, maybe not today. One thing I did want to show you is, this is the Maillard-Le Chatellier result you would get for a gas phase flame, burn in terms of the flame speed, if you go back to a simple combustion book. Again, you'd find the laminar flame speed is proportional to the thermal diffusivity times the reaction rate to the 1/2 power. This was the equation that we derived today, showing the burning rate depends on the reaction rate, again, to the 1/2 power. The big difference here, this is the gas density, this is the solid propellant density. Okay, this is going to be a strong function of pressure. This is not a strong function of pressure. So what you typically see, if I take the ratio of, say, R sub B over S sub L, and I take a ratio of these two equations, if I go to very high pressures, what I'm going to find is, if I could vaporize, for example, nitromethane, and look at just the vapor flame speed, and I could look at the condensed flame speed of the liquid, what I would find as I go to very high pressures, I'm going to get this equation here. So all of a sudden, if I go to very high pressures, the density of the gas is going to approach that of the solid phase. So this is going to go to unity. As I go to very high pressures, I could all of a sudden lose the surface characteristics because of the real gas effects and basically going from transcritical to supercritical burning. So this term could go away here. Then all of a sudden, I'm going to find the first approximation. The laminar flame speed should be the same value as the flame speed of a liquid burning. And I'll show you that later on. Okay, I'll stop after this slide here. I just want to, if I look at the burning rate as a function of pressure, remember I told you the value of N can change. So, and one basically gives names to the characteristics of those profiles. So here's 3 examples. This profile here has a plateau, and then it increases again. So this is a plateau burning propellant. This profile here actually goes negative like the AP. This is referred to as mesoburning propellant. And this one here actually sort of extinguishes in a pressure range before it reignites intermittent extinction. Plateau burning is very favorable, because if I can run my motor in this region here, then all of a sudden if I have an excursion because of a pressure fluctuation, suppose all of a sudden a little crack or a void appeared at the surface that wanted to increase the pressure, then this is going to say the burning rate's not going to depend on it. Okay? And one of the goals today is, can I design propellants that would extend where this last break occurs so that I can even operate at higher pressures? Okay, so let's stop there. I'll pick up a few more notes here. I think I have some photographs of burning propellants in movies I want to show you, and then we'll start looking at the addition of metals tomorrow and things.